Temperature. You ever thought about what temperature is? You might say, oh, my little brother has a temperature. That's kind of silly, isn't it? We all have a temperature. You mean he has a fever. But why are some things hot and some things cold? It has to do with the motion of the molecules and atoms that make up the matter. They're in constant motion, like we mentioned before, and that's thermal energy. The temperature of a substance is a measure of its thermal energy, how much those particles are moving. If you take a solid substance like an ice cube and you begin to warm it up by putting energy into it, you cause the molecules in the water to move more. So that would be like putting energy into you guys, maybe giving you all a rock star. And, and now you're like wiggling in your chairs and you're tapping your foot and you're bouncing your legs. You just can't sit still because you've got too much energy, right? And eventually they're just going to start moving even more and the solid will melt into a liquid. The temperature is a measure of that thermal energy. So the hotter an object is, the more motion its particles have. If the object is colder, the molecules are slower. And so I think of this in terms of people walking barefoot on the beach. If you go to Pismo in the summer, it's like always overcast and cold, which is why we go there, because that's refreshing for us. It's not what most of the country thinks of when they think of going to the beach. Foggy and windy and cold. It's fabulous. So you're walking on the beach, and the wet sand, nice and comfortable, you're just strolling along, right? Now, what if you went to Reedley Beach? You guys ever been to Reedley Beach? Have you heard of Reedley Beach? Okay, the Kings River runs through Reedley, and there's this big sandy area. It's a beach on the river, right? Okay, you can imagine what this dry sand feels like when it's 115, right? The sun's beating down. Are you going to stroll along that hot sand? No, you're going to run as fast as you can to the water. And the reason people go to Reedley Beach is not because of the sand, it's because of the cold, cold water. So when something is hotter, it's like barefoot people on hot sand. They're going to move quickly. We say they hot-footed, right? Because it's hurting your feet. And if something is colder, it's going to move slower. So all matter, if you cool it down, you're slowing down the motion of the particles. If you warm it up, you're increasing the motion of the particles. So temperature is a measure of the thermal energy of the matter. It's important to keep temperature and heat separate. They're not the same. Heat does have units of energy, but it is a transfer of thermal energy. You only have heat when it's moving, when you have thermal energy moving from one thing to another. The ice cube in your hand. There is heat being transferred. There's thermal energy from your hand being transferred to the ice cube. Your hand is getting cooler, the ice cube is getting warmer. Or you drop a piece of ice into a cup of warm water. There's heat flow. Thermal energy is transferred from the warm water to the cold ice. The temperature is the measure of thermal energy of matter. So you can measure the temperature of the water. You can't measure the heat of the water. Heat is the transfer of thermal energy due to temperature difference. Any questions? We're tiptoeing into physics in this chapter in a couple different areas. This is really more physics than chemistry. Temperature scales. There was a little bit of this in that first lab we did, but now we're going to really talk about temperature scales. So there's three main temperature scales. Fahrenheit is what you're most familiar with. The weatherman, says it's going to be 57 degrees. He means 57 degrees Fahrenheit. On the Fahrenheit scale, water freezes at 32, boils at 212. Is this a metric scale? Nope. Weird numbers, huh? English units always have these just kind of random numbers. Celsius scale is also sometimes called the centigrade scale, which means hundredths of a gradation. On the Celsius scale, water freezes at 0 and boils at 100. That sounds more metric, doesn't it? And then the room temperature would be approximately 22 degrees. The Kelvin scale, avoids negative temperatures. And we needed to use this a little bit in that first lab because we were finding a percent error of a freezing point. And the actual, or the accepted freezing point was 0 degrees Celsius. And you can't divide by 0. So when we have zeros and negative numbers with temperatures and we do certain types of calculations, things don't work out very well. The Kelvin scale is such that all temperatures are positive. And it does this by assigning 0 Kelvin, which, it looks a little bit like okay, but it's not. 0 Kelvin is the coldest temperature possible. We call that absolute zero. Absolute zero is a theoretical temperature at which the motion of particles would stop. They wouldn't even be wiggling. They would be completely still. To my knowledge, no one has ever achieved a temperature of 0 Kelvin. They're trying. They've gotten close. But they can't get it to actually stop. So here's a graphical comparison of these temperature scales. Fahrenheit, 212 down to 32. Between the boiling point of water and the freezing point of water are 180 Fahrenheit degrees. Over on the Celsius scale, we assigned boiling to be 100 degrees and freezing to be 0. And I think they did that because those temperatures are easy to achieve. Pure water at sea level boils at 100 degrees Celsius. It freezes at 0 degrees Celsius. Almost anybody could reproduce that. You don't need special equipment. Because really, how do you define the starting point for a temperature scale? You just have to choose something. So that's what they chose. And they said, okay, well, between boiling and freezing, we're going to divide that into 100 degrees. And this is going to be a real nice, convenient temperature scale. And it is for a lot of things. But then sometimes we can't have those negative numbers. So the Kelvin scale also has 100 divisions between boiling and freezing of water. But now, I keep pointing on the wrong thing. Now, 0 is absolute zero, the lowest possible temperature. So what we are familiar with as the freezing point of water is 273.15 kelvins. And these units are kelvins, they're not degrees Kelvin. It's easy to slip and say degree, but they're not degrees at all. But a Kelvin, there's 100 kelvins here and 100 Celsius degrees. A Celsius degree and a Kelvin are the same size. They're just offset from each other by 273. Minus 273 Celsius is, I don't even grasp that. Because, Celsius we just don't have a good feel for it. Fahrenheit, minus 459 degrees Fahrenheit. That's really cold, isn't it? That's crazy cold. I grew up in Minnesota, and there were some days when I was a kid where it was minus 40 degrees Fahrenheit. And that was not the wind chill, that was the actual temperature, minus 40. And that's, even now it's hard for me to, we didn't go outside, so we didn't feel it. Your skin freezes in like 3 seconds at minus 40. But this is minus 400. That's just crazy, crazy cold. So anyway, those are the temperature scales. So if we have these different temperature scales, we have to convert between them. Temperature is something that we cannot use dimensional analysis for. Dimensional analysis does not work for everything. It does not work for temperature. So we need to use these equations. The temperature in Kelvin equals the temperature in Celsius plus 273.15. The temperature in Celsius equals the temperature in Fahrenheit minus 32, that quantity divided by 1.8. So let's do some examples. Yeah. I think I can. There it is. There it is. So those are important equations. Got it? And these slides are on Blackboard if you want to look at them or print them out, or print them out and throw darts at them or something. I don't know. So we only have one number here. A pretty straightforward problem. Convert this to this. Convert 358 Kelvin to Celsius. Well, temperature conversions, we need an equation. So the Kelvin temperature equals the Celsius temperature plus 273.15. Why is it 273.15? It just is. So we take we have our equation, and this is going to give us the Kelvin temperature. But we want to know what the Celsius temperature is. So we need to rearrange this equation. So there's different ways to represent that. One way to do that is this way. So I'm going to subtract 273.15 from this side of the equation. And so 273.15 minus 273.15 is 0. And so I end up with just degrees Celsius on that side. If I subtract that from one side, I have to subtract it from the other side. And then what do I end up? I end up with Kelvin minus 273.15 is equal to Celsius. That's rearranging equations. Sometimes students have trouble with these simple ones because I guess you just can't believe that it's really that easy. And yeah, sometimes it is. Not everything is hard. Okay, so degrees Celsius equals Kelvin, which is 358 minus 273.15. 358 minus 273.15. Calculator says 84.85, and that would be degrees Celsius. Then we're always going to look at our significant figures. So the number 358 has uncertainty in the last digit, and 273.15 has uncertainty in the last digit. We're subtracting, so we're looking at number of decimal places. So this one has uncertainty in the ones place, and this in the second decimal place, hundredths. So our answer is going to have uncertainty in the ones place, right here. So we're going to round that and call it 85 degrees Celsius. Any questions? Let's do another one. Convert Celsius to Fahrenheit. Can't even read today. 139 degrees Celsius. There's the number. Well, what equations do we have available? We've got that Kelvin equals Celsius plus 273. That's not going to help. The other one is degrees Celsius. Actually, I'm going to move this over because I'm going to have to do some rearranging here. Degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. We need to know what Fahrenheit equals, so we have to rearrange this equation. The basic idea in rearranging equations is that you undo what's done. So here we've got Fahrenheit here. This is what we're trying to get by itself. Well, what's been done to the Fahrenheit? It's had 32 subtracted and 1.8 divided. We need to do the 1.8 first. If we multiply this side by 1.8, the 1.8's cancel out. If I do it to that side, though, I have to do it to this side. It's still equal. Now I've got Fahrenheit minus 32 is equal to 1.8 times the Celsius temperature. Well, how do I get rid of minus 32? I add 32. Oh, what's that about? Add 32. Because 32 minus 32 is 0, and adding 0 doesn't do anything. If I add 32 to one side, I have to add 32 to the other side. So that's kind of a messy thing, so I'm going to rewrite it. The Fahrenheit temperature will equal 1.8 times the Celsius temperature plus 32. And I switched the order there just because it makes it more convenient to do on a calculator. Because 1 plus 2 is the same as 2 plus 1. Now I have an equation for Fahrenheit. I can just plug in the Celsius. So 1.8 times the temperature in Celsius, which was given as 139, plus 32. I use my calculator, 1.8 times 139 plus 32. Calculator says 282.2. That would be degrees Fahrenheit. Because these conversions involve an equation and not dimensional analysis, you can't cancel units and do all that awesome stuff. You just have to know what the unit is at the end. This is one of the very few situations where we end up with stuff like that. And then, how many significant figures should this have? Well, that gets a little tricky, doesn't it? We've got multiplying and adding. So we could work that out, but there's some funny things that happen with certain combinations. And so, just as a rule of thumb, whatever uncertainty you had in your starting temperature, here it's in the ones place, then you should have that same uncertainty in your final answer. So we're going to round this to 282 Fahrenheit. We're essentially using the adding, subtracting rule and going with the number of decimal places as opposed to the number of significant figures. And the reason for that is that a Celsius degree is 1.8 times a Fahrenheit degree. Yes, that's almost twice as big, and yet they're still pretty similar in size. It's not like it's 10 or 100 times larger. So if you had uncertainty of 1 degree Fahrenheit, that's very similar to an uncertainty of 1 degree Celsius. Any questions? Here's another one. Convert minus 321 degrees Fahrenheit to kelvins. So there's the number we're dealing with. Were we given an equation relating Kelvin and Fahrenheit? No. We're starting with Fahrenheit, we're ending with kelvins, but we don't know the relationship between them. We do know the relationship between Fahrenheit and Celsius, and we have an equation for Celsius and Kelvin. So I'm writing a path here, not because I'm going to do dimensional analysis, but just to plan out what conversions I'm going to do. I'm going to take my Fahrenheit temperature and convert it to Celsius using the equation. Then I'm going to take the Celsius temperature and convert it to Kelvin using the other equation. So Fahrenheit to Celsius, degrees Celsius equals degrees Fahrenheit minus 32, that quantity divided by 1.8. So in here I'm going to put my minus 321 and minus 32 and divide by 1.8. Be careful with those minus signs. Now watch your display. Some of your calculators don't do this, but if you have like a TI-30XA or any one-line display calculator, you can watch it. So I'm going to put in 321 and change the sign to make it negative. Then I subtract, nothing happens when I push the minus button, and then I press 3, 2. Now, if I push the divide button, what happens? It's still showing me 32. It's going to divide 32 by 1.8. That's not what I want. I want minus 321 minus 32, the whole quantity. So what I need to do is do the 321 negative minus 32 and press the equal sign. Now my calculator is showing me minus 353. That's the quantity. I forced it to finish the subtraction. That's how I prefer to do it. The other thing is you could use parentheses. Now I'm going to divide by 1.8, and I'm going to get minus 196.111111. So make sure that you can get your calculator to do that. That's repeating, and that is degrees Celsius. Any questions? Now I'm going to take that number and convert to Kelvin. Kelvin equals degrees Celsius plus 273.15. So I'm going to take that minus 196.111111, and I'm going to add 273.15. I have that number still in my calculator. I'm just going to add plus 273.15. And this tells me that the Kelvin temperature is 77.038, and those 8s are repeating. Kelvin. Is your calculator cooperating? And then how should we round that in terms of significant figures? Well, what was our original number? 321. Okay, so we have to go way back to the beginning. 321, and that was to the ones place, right? So then this should be to the ones place. So we'll call this 77 Kelvin. A Kelvin and a Celsius degree are exactly the same size, and a Fahrenheit degree is less than half. I mean, it's smaller, but not that much. Math in my head. Any questions? You should be able to do these sorts of temperature conversions.